Hi, this is another video in the tutorial Trees-Based Methods. This is the course Digital Economy and Data Analytics. My name is Eik van Vuren and I would like now to go on with the last topic of this tutorial, and that is the topic of boosting. At the moment that we would like to do boosting, then we have to, import this gradient boosting regressor that we have over here, that we can import another time from the library sklearn. In this case, we are going to look at the sklearn.ensemble. So in total, we're going to have from sklearn.assemble, we're going to import this gradient boosting regressor. At the moment that we are going to introduce this gradient boosting regressor, then we have to introduce some values, and the most important value that we have to introduce is a so-called learning rate. Remember that at the moment that you're going to do gradient boosting, as I explained during the lecture series, it implies that you're going to do a couple of different steps. You're going to do actually many steps. You start with a, say, very bad predictor, and you're going to update that predictor all the time. And the speed in which you're going to update it, that is determined by this learning rate that we have over here, and that we actually have to set. And that implies that one of the options that we're going to have over here is that we set, in this case, the learning rate equal to 0.2. Well, the default is actually 0.1. We are going to set it here a little bit higher, but take into account that this is, again, just for illustration. It's just a random number that I've chosen over here. The number itself isn't that important. It's just for illustration, because of the fact that later on what we need to do is, of course, cross-validation. But that is going to be for the next slide. Take into account that we can also look at other things. Apart from learning rate, we can also look at the max depth. And that is related to the fact that even though we do know that boosting can be done for any kind of, say, algorithm, any kind of algorithm can in that sense be boosted, we should realize that in most cases we do that actually with respect to decision trees. And that's also the case over here. This gradient boosting regressor is actually related to regression trees. And therefore we have to determine, well, what is in fact the maximum depth with respect to our tree. And here we are going to allow it to have, say, 3 different layers. Well, that's actually also the default. So officially, I didn't really have to set this max depth over here because of the fact that then it would actually also be equal to 3. But take also into account that we could have, of course, set this a little higher or a little lower. If we, for example, set it equal to 1, well, then actually the boosting process will essentially be somewhat slower in a sense, because of the fact that that implies that we are going to have, really, say, not that great predictors in the boosting process, because of the fact that then we're going to get trees of only 1 layer. But take into account that actually the boosting process itself will be faster in terms of computer time. So therefore we could at least do more steps and then in the end reach to the same ID. Well, it isn't that clear yet right now how large we have to set this thing over here, whether we have to set it equal to 3 or 1 or 6 or maybe even larger. But we set it here equal to this, at least to start with it, we set it here equal to 3. Well, then after we have introduced this gradient boosting regressor, we're going to, then store it into this variable CLF that we have over here. And then the next thing that we need to do is that we have to fit it, and that we always do with clf.fit. And then we have to, of course, do that with respect to the training data set. So therefore, first of all, xtrain, they are going to be the x values of our training data set, and ytrain, they're going to be the y values of our, say, training data set. And we're going to store that in this fit that we have over here. Well, then on the next slide, we would like to look a little bit more into how we are going to cross-validate, or how we are going to do the cross-validation process. And for that, as usual, what I'm going to do is I'm going to look here at the full program. And if you're going to look at the full program, then the first thing that we're going to see, as usual, is that we are going to do some imports. Most important import actually is over here. We have to import, of course, this gradient boosting regressor. Well, then next to that, we are going to look at some different constants. well, the constants that we have over here, they're a little different from what we have seen before. For example, we have here the minimum learning rate. We set that equal to 0.1, and we have a maximum learning rate equal to 0.8. Well, as you might already expect, then what we're going to do is that we're going to, well, search for the optimal learning rate in between 0.1 and 0.8. Well, this thing is quite important. The n estimators, we're going to set it here equal to 1,000. And these n estimators are actually the number of boosting steps that we're going to take. So again, boosting actually starts with a very bad predictor. Then it's going to update. Then we are going to do the first step. It's going to update again, second step, etc. And at a particular moment in time, you simply stop with respect to boosting. And well, the number of times you're going to do that, that is determined by this n estimators that we have over here. The default in this gradient boosting regressor is equal to 100, but that is actually not that great. Usually it's much better to set it a little higher and to set it at least equal to this 1000 that we have over here in order to get a, say, better prediction. After 1000, usually it doesn't work that much better anymore. It only takes more time, of course. So therefore, well, these n estimators usually have to set it quite high, but maybe not too high because of the fact that also it may take you a lot of time. Well, then another thing which is important here is this depreciation rate that actually says how quickly we actually go down with respect to this learning rate that we have over here at the moment that we're going to search for the optimal learning rate. And we have here this depth. That's of course the maximum depth that we are going to have with respect to the trees on which we're going to do boosting. Well, take into account that officially this is also an hyperparameter, so therefore it would have been best that we are going to do, say, cross-validation both on the learning rate as well as the tree depth. However, that is going to take quite a lot of time, so therefore here I have decided just to take a depth equal to 3. Of course, what we could have done if you really would like to do it correctly is to do cross-validation both on the, say, the depth as well as the learning rate at the same time. But that is not what I did over here. Then if you're going to look at the cross-validation, then the first thing that we're going to see is here this function that we have over here. That's a function that we have already seen before because of the fact that we have introduced already this, this do cross-validation function before. It's exactly the same as what we have seen before. In some of the applications that we have been looking at during these videos, we didn't need it. Well, more particular at the moment that we did backing random forest with out-of-back samples. But now we're not going to do out-of-back samples, cannot be done actually with respect to this boosting. So therefore, we still are going to use this do cross-validation that we have over here. But it's not different from what we have seen before. So therefore, I decide not to talk too much about it. It's better to talk about this function that we have over here, the cross-validation function. It's a little different from what we have seen before, apart from the fact that it takes the number of folds and the X train and Y train. It also is going to take as arguments the min learning rate as well as the max learning rate. Well, we already know what that actually is. And then at the moment that we are going to look at the body of this function that we have over here, then most important here is that we start here with the learning rate, setting the learning rate equal to the maximum learning rate. So essentially what we're going to do, and that's quite like what we have seen before with respect to lasso and ridge, at the moment that we are going to set the alpha, is that we start with a high learning rate and we're going to go down to lower learning rates. So therefore we're going to have this while loop over here which says while learning rate is larger than the minimum learning rate. Well, for our first loop that we're going to take, we should realize that that's of course always true because of the fact that we have just set the learning rate equal to the maximum learning rate. And given the fact that the maximum is of course larger than minimum, we are now higher of course than the minimum learning rate, but also take into account that every time that we're going to loop through this, we are going to decrease the learning rate by this say value that we have over here, this percentage that we have over here, 1 minus the depreciation rate. Well, that was equal to 0.2, so we're going to, well, take every time 80% of the original learning rate that we had before. So that implies that this learning rate is going to decrease and decrease and decrease all the time. And at a particular moment in time, it may actually be lower than this minimum learning rate that we have over here. And of course, then our procedure is, or at least this loop is going to stop. Then if we're going to look in this loop, then we are going to first of all look at the gradient boosting regressor. Well, we're going to set there the maximum depth, also the learning rate. We're going to use this random state in order to, well, make our results reproducible. And then finally we're going to have here our n estimators that we're going to set equal to the n estimators that we had before in our constant and in our list of constants. And we already know that that's of course equal to 1000. And of course this learning rate that we have over here is equal to the learning rate that we use over there. Then we do the actual do cross validation. That is this function that we have introduced before. So this function that we have over here. Essentially that function simply is going to give us the cross validation risk here denoted by the CV that we have over here. We print it out. We are going to, well, in fact store it in this result in alpha 2. And then finally what we're going to do is that we're going to pick that, value of the learning rate that is going to give us the lowest cross validation risk. Well, then we get to our main function. Well, that's almost identical to what we have already seen a couple of times before, but still, let me look at this. Here we are going to set the optimal learning rate by doing cross-validation. It doesn't really say optimal learning rate, but I just call it here learning rate itself. And then after having that optimal learning rate, we are going to do one more gradient boosting regressor, of course, in order to, well, get the to be able to predict. So, and then in this case, of course, with respect to the optimal learning rate, we're going to fit it and then predict it. That is, of course, with respect to the x values of the test sample. So that is this part that we have over here. Then we calculate the mean squared error. We're going to calculate also the total sum of squared residuals, and that gives us the opportunity to print out the mean squared error. In fact, nothing else as the test risk. And we can then also calculate the r squared, or print out the r squared among the test sample. And then finally what we still need to do is to have these two lines that we have over here. Well, then at the moment that we're going to run this, actually we should realize that this is actually not so bad, because of the fact that at the moment that we're going to then look at the test risk, well, the test risk then becomes equal to 0.0193. And the corresponding r squared for the test sample is then equal to 0.9332. Well, remember that Ridge was so far the best performer that we had so far. It had a little lower than 93% explained of the total variation with respect to the prices in the test sample. We do see that actually boosting does here even a little bit better. And that is to say that boosting usually is a very good method to make predictions, actually both in classification as well as in a regression context. So in that sense, this well, just underlines once more that boosting is actually a very good and powerful method. However, one problem with respect to boosting is that it actually takes quite a while, even in the moment that the data set is not that large, and that's actually true for our case. At the moment that you're going to run this thing that we've over here, we only have a couple of thousands observations, but take into account that this actually took quite a while, at least on my computer. Now, I do not have the fastest computer, but take into account that even if I would have had a much faster computer, this would actually have taken me a while. However, there is an alternative, and that is that there is actually an OpenMP version of the gradient boosting regressor. What actually is true with respect to the gradient boosting regressor is that it only uses one processor on your computer. And take into account that most computers actually do have, well, most of them, they actually have at least 8 different processors, and there are quite a lot of computers that have many more processors than just 8. So therefore, it is a little bit of a waste of time in a sense if you're going to only use one particular processor on your computer if you have many more of them. So therefore, there is a multiple processor version of this gradient boosting regressor, and well, there are a couple of them, but one of them is also an sklearn, and that is this hist gradient boosting regressor. It works almost identical to what we have seen before. However, then of course what you need to do is to not import the gradient boosting regressor, but you have then to import this hist gradient boosting regressor. And apart from the fact that you of course have to change this line in the program that I have showed you on this previous slide, another thing that we have to do then is that we also in fact have then to change, of course, the line that introduces the gradient boosting regressor, because of the fact that there we also need hist gradient boosting regressor. Well, all the options are exactly identical, with the only a little bit annoying difference is that n-estimators is no longer called n-estimators, but it's now called max eta. But apart from that, everything is exactly